Okay, so we've seen two gas laws. We've seen Boyle's law, which was pressure and volume when temperature was remaining constant. We've seen Charles's, which was volume and temperature adjustments when pressure was constant. So obviously the third variable is remaining volume constant, Gay-Lussac. This is Joseph Louis Gay-Lussac. Joseph Louis is a Frenchman as well. Late 1700s into the 1800s. And French, obviously, they're pretty smart. Just see me. A little humor. Try to make it through the day. So, see Marquis. And he described also a law that, he came out with a law that described ABV, the alcohol by volume. Okay, so volume and the alcohol, percentage of alcohol by volume. So, some things that he was known for. I don't know if anyone noticed I used the wrong spelling and the wrong word there. I thought you might find that amusing, as I was saying they're pretty smart and I used the wrong one. It's funny to me. Anyhow, Gay-Lussac, he said that if a volume remains constant as the temperature of a gas increases, the pressure will also increase. Okay, so in this situation, Gay-Lussac basically was saying, okay, volume remains the same, and I'm not going to go over great detail. It's very similar. Volume remains constant. As the temperature, the pressure will also go up. Okay, so this is similar to Charles's law, where they're direct relationships. As one goes up, the other goes up. Again, so if you have a first situation, a pressure 1 and a temperature 1, then and compare them to P2 and T2, whoops, that's a 2, okay. If the pressure is 1 atmosphere and the temperature is 100 K, if you increase the temperature, let's say we increase it to 200 K, then the pressure would also increase. And I'm going to write it in a different color. Let's say that we were solving for it would also increase and would go to 2 atmospheres. Same type of formula as Charles's, since it's a direct relationship. You would say the P1 over the T1 equals P2 over T2. Again, notice 1 over 100 is the same as, and if I write underneath here, 1 over 100th is the same as 2 over 200. Okay, so it's a way of showing two similar fractions. I am a fan, again, if you need to solve for any of these variables, if P2 is what you were looking for, before I would have done any solving, I would have cross multiplied P1 T2 equals P2 times T1. Then you want to solve for P2, you would then divide both sides by T1. P2 equals P1 T2 over T1. And that would be the formula if you wanted to solve for that one. Gay-Lussac's law, though, again, if I write it down, P1 T1 equals P2 T2. And again, I'm a fan of getting that cross multiplication to get denominators out of there. It's very easy if I'm solving for this one. I just would multiply both sides by T2, and there's my formula. But what I see people have a lot of trouble with is if I'm solving for the temperature, because it's in the denominator, sometimes they miss it, they miss the reciprocal, they take the wrong formula, and they have some trouble when they calculate. So again, I'm a big fan of that. I do have another quick little video that kind of relates to this. It's a cool little video. It's a demo I've done before in my classroom. Well, let's take a look at it. So here was the law again, but let's take a look at this demo. It's in slow motion here. A lot of people think that the egg is sucking in the air, but that's not the case. What we're doing is we're increasing the temperature. We're increasing the air, the flame, and the air cools, or because the air cools, then the pressure will decrease. That means the atmospheric pressure is more and it'll push it down. Here, how do you get the egg out? You increase the temperature of your air on the top of your egg. Increasing the temperature of that air is going to increase the pressure, and notice it's going to be able to push the air out. Increased temperature increases the pressure, and it pushes it out. Okay? Oh, this is a pretty cool little, he continues with a smaller mouthed container. And your egg gets shattered. Good stuff. We can go slow motion again. There it is. And again, that's going into the bottle because atmospheric pressure is greater than the pressure inside because it cooled down. So there's Gay-Lussac's law.